This is an example of a hard level problem in the Bode Plots game in Circuit Tutor. Notice that we can always view examples at various levels of difficulty, and it's strongly recommended that you do view some examples prior to attempting the exercises, as that'll make it a lot easier to complete the exercises successfully. Also, we recommend, of course, that you, if you have not already done so, view the introductory tutorial on Bode Plots, which is available on the main game menu. Okay, so let's do a hard level problem. And so this is giving me a randomly generated transfer function here. And the first task is going to be to find the limits of this transfer function, both as omega goes to 0 and as omega goes to infinity. So by inspecting this now, as omega goes to 0, this is going to give me, this goes away, and so I just have 100 squared. So that's going to cancel out 0, 0, 0, 0. That's going to give me 32 in the numerator. And then as omega goes to 0 here, these both go to 0, and so I have 32 divided by 16, so that's going to be a value of 2. And if necessary, of course, you can use a calculator to do that, but this one is pretty easy. Okay, then as omega goes to infinity, there's no omegas in the numerator in this case. We have no zeros in this transfer function. Therefore, that's pretty straightforward. As omega goes to infinity, the denominator clearly blows up. Again, if we needed to, we would just look only at the highest power of omega, which would be this power here, so that would be omega squared. And then this also has an omega squared, because again, for large omega, this would become much bigger than these other two terms. So overall, this would be omega to the 4th. And then if you had some omegas up here, then you could figure out which one would cancel out and what would happen to the final value. But here it's quite obvious that as omega goes to infinity, this goes to 0. Okay, and if you need to enter infinity for any of those results, then you just click on these buttons like there, for example, and that would put an infinity character for you in there. But I'll put back 2. Okay, so the next task now, since we've done that correctly, is to identify the type of filter. So we see that this filter indeed passes low frequencies with a gain of 2, but for very high frequencies, it does not pass them and has a gain of 0. So that would be a classical low-pass filter, because it's passing the low frequencies and rejecting the high frequencies. If both of these limits were 0, that would typically indicate that it's a bandpass filter. If both limits were, say, some constant, which in our problems here would probably be the same constant, then that would be likely a band stop filter. Okay, so this is going to be a low-pass filter, and then we have to identify the order of this filter. And if we look at the transfer function, we have here a double pole involving a real pole, and then we have another double pole that is going to be a complex conjugate pair. Typically, they're not written in this quadratic form here, if they can be factored the way this one was, so or factored into 2 different terms. So that indicates that's going to be a pair of complex conjugate poles, although we can figure that out, and we will figure that out a little bit later. So we have a total of 4 poles in the denominator here. So therefore, that's going to be what we call a 4th order filter, and that requires, in other words, 4 reactive elements in order to realize that transfer function. If we're going to build a circuit that would actually have this desired function, it would take 4 reactive elements. So let's check that. And that is correct. And of course, that higher order filter is useful if you want to get a steeper cutoff in the filter, as opposed to a low order filter would have a rather shallow cutoff. Okay, so now the next task here, and there's a little bit of explanation there, it's been added, but basically our next task is to put this transfer function into what we call standard form. So in standard form, basically each additive term where we're adding things together, the constant needs to be set equal to 1. Now that doesn't apply to terms that are just multiplying things, like if this added j omega next to it or something. Those don't have to be modified. But these terms, basically what I want to do is pull out 100 squared out of this one to make this constant 1. And here I need to pull out a factor of 16 to make this constant 1. So that's how we put that into standard form. So because this is a ratio, I will need, first of all, a fraction term, which is this term here. And I can either click on that, or I could also alternatively drag it into position, click and drag. And you can also drag them out of position just by pulling it out of that equation entry area. Okay, so in the numerator, we're going to have a constant. So I'll just select that little numerator area. I can just click on that. It's probably an easy way to put it there. Or I could have just drug it and put it where I wanted. But again, I'm just going to use the click method. And then in the denominator, we need a term like this, which is going to be basically 1 plus j omega or something squared. So that's going to be this type of term. So I'll select the denominator and just click that. Or again, I could have just drug it down in the denominator like that. Okay, so that's going to be squared. So let's do that. And that term, when I factor out the 100 quantities squared, that's going to be 1 plus j omega over 100 quantities squared. That's how I make that constant term 1. And that means I basically pulled out a factor of 100 squared, or 10,000. Okay, so that's going to basically get rid of the 4 zeros there and leave me with 32 in the numerator. But I won't put that in yet because I'm not done with this other one. Okay, so now here, this is a quadratic term. And as I said, it's going to be a complex conjugate set of poles. So basically there, I need this type of, that's the standard form for this. It would be 1 plus 2 zeta, that's the Greek letter zeta, times j omega over omega naught, plus j omega over omega naught quantity squared. So I'm going to need to use that term in the denominator. So I'll click that, or I could have, again, drug it into position if you want to drag it down there. And so this one I have to use a little bit of care in filling this out. First of all, I know this is going to be 1, so I've basically divided by 16. So this has to be in the specific form, j omega divided omega naught quantity squared. So I have to start with this term. You can't start over here because you won't know what omega naught is, basically. So you have to start with this term to determine omega naught, because this other term, the coefficient depends on both zeta and omega naught. So you can't figure that out by itself until you know omega naught. So basically, if I divide by 16 and put that inside the square, that's going to be a j omega over 4 quantity squared. Okay, and so that tells me that my omega naught here is 4 radians per second. Now I have to enter the same exact value to make the standard form in both of these two entry fields. If I enter something different over here, when I go to check it, it's just going to tell me that I've put it in the wrong format. And what that does, basically, it makes your value of zeta incorrect, and it won't give you accurate information on the damping. So this has to be the same as that. So you have to figure it out here, and then you'd use the same value here, because that's the nature of the standard form, is it has the same denominator in both cases. Now I need to figure out what zeta is. And if you think about it here, I have 6.4 here. I have to divide that by 16 to make this constant 1. So 6.4 divided by 16, that's going to be 0.4, right? Because 64 over 16 is 4. So that's going to be 0.4. And so this altogether needs to give me 0.4. Well, 2 divided by 4 is 0.5. And so this will have to be a 0.8, I believe. So just checking that, 1.6 divided by 4. I'll just double check that real quick to make sure I didn't make a silly mistake there. And that is indeed the 0.4. Okay, and then the 6.4 divided by 16 again is the 0.4. So that will be correct. And now I have to just figure out the constant on top. So again, when I pulled out the 100, because that's squared here, that's really a factor of 10,000 that I pulled out here. And that canceled out 4 of the zeros there. And so that leaves me with 32. And then when I pulled out the factor of 16, of course, then I have 32 divided by the 16. So that's just going to be 2. So the numerator now is just a constant of 2. So that should be the properly standardized form, and that is correct. So again, just be careful of those quadratic terms that you find omega naught first before you try to find zeta. You can't find zeta until you've worked out omega naught, which you get from this term. Okay. Okay, so now the next task is to take the magnitude of this complex valued transfer function, because after all, we're trying to do a Bode magnitude plot here. We could also do a phase plot, but Circuit Tutor doesn't currently deal with phase plots since they're not quite as important as the magnitude plots. So we have to take the magnitude of this, and what we notice is that this is a quotient of two things, and that means we have to use one of the basic rules for taking magnitudes, which is the magnitude of a quotient of two complex numbers, is the quotient of the individual magnitudes of the numerator and denominator. So the magnitude of the quotient is the quotient of the magnitudes. And that means that I need to separately take the magnitude of the numerator and the denominator. Well, the numerator is real easy because that's just a real number, and it's positive, so its magnitude is just the number. If it were a negative number, of course, the magnitude of a real number is the same as the absolute value. Remember, well, it's the square root of real part squared plus imaginary part squared. So it's the square root of this number squared, which would be its absolute value. So if this happened to be a negative number, then you would have to take its absolute value. Okay, then in the denominator, I actually have a product of two terms, and I need to take the magnitude of that denominator. So when I take the magnitude of a product, much like the magnitude of a quotient, that is going to be the product of the magnitudes of the individual terms. Now, why is that? Well, it follows directly from the way that you do complex multiplication. Remember that if you have two complex numbers in polar form, like magnitude of z1 e to the j theta 1 times magnitude of z2 e to the j theta 2, then you would just multiply the magnitudes, and then the phase angles would add because it would be e to the j times theta 1 plus theta 2. So that basically proves that the magnitude of a product is the product of the magnitudes, and the same token for the quotient. If you divide two complex numbers, magnitude of z1 e to the j theta 1 or magnitude of z2 e to the j theta 2, then you would just divide the magnitudes, and then you'd have e to the j times theta 1 minus theta 2, right? That would be, or the quantity rather. So you subtract the phase angles basically. But we're interested here in the magnitudes, so we just use that rule. Now for each individual term, like this one for example, or this one, we have to use the rule that the magnitude of any complex number is the square root of the real part squared plus the imaginary part squared. Remember, the real part is whatever does not multiply j, and the imaginary part is whatever does multiply j. Now, very important to remember that the imaginary part of a complex number does not include a j ever, because the imaginary part is by definition a real number. Remember, a complex number is an ordered pair of real numbers. So the imaginary part of a complex number never includes a j. It's always a real number. And if you include a j, you'll get the wrong answer very dramatically. So, okay, so in order to find this magnitude now, we know it's a fraction. So let's start out by putting in a fraction term here, which is this first term on the left. And the numerator, well, that's really easy because that's just going to be 2. So we could just put a 2 there and fill in a 2. Again, it's the absolute value, whatever that number is, since it's just a real number. And then in the denominator, this part, I'm going to have to use a bracket or a power. So I'll put a bracket in there to raise that to a power. And if it were just 1 plus j omega over 100, it would be the square root of the real part squared plus the imaginary part squared. The imaginary part would, of course, be omega divided by 100, because that's what multiplies j. However, this entire term is squared as a double pole, and therefore I'm not going to take its square root. I'm just going to put it to the 1 power. So I'll put a 1 there in the exponent. That's basically, I just need the brackets to group the terms together. And so let's just do that part first. So the real part squared, well, the real part is just 1. So 1 squared, of course, is 1. So I'll just select that little inner area there so it's highlighted, and I can just click the 1, make it real easy to put it in place, plus, and then I need the omega over omega naught squared. So again, I just click that, although again, you can also drag in a position. But so in this case, that's going to be omega divided by 100, and then that's going to be squared. So that's our first term. Again, there's no square root here because this is squared. So the square root gets squared basically, and it's just to the 1 power now. Now for this part, we will need another bracket. So I'll bring that down here. And this one indeed will be a square root because we have both real and imaginary parts. Now this one's a little bit trickier because now we have to think, well, what's the real part of this number? Now you might be tempted to say, oh, it's just 1 because everything else has j's. But you have to be more careful than that because this part indeed has a j, but here the j is actually squared. And j squared, remember, is not a complex number. It's a -1. It's a real number. So this really, when we square it, is going to be negative omega over 4 quantity squared. And so the real part of this whole thing is basically going to be 1 minus omega over 4 quantity squared. So we're going to have to put a bracket inside a bracket to deal with all that. And again, this would just be a 1 power. And so we're going to have, in there, we're going to have the 1. So I'll just select the interior of that. So 1 minus the omega over omega naught squared. So that's going to be over 4 quantity squared. And then, sorry, I'm sorry, that shouldn't have been a 1. That should be a 2 because, again, that's the real part squared. So this is basically the real part is 1 minus omega over 4 quantity squared. And then out here now I have to put the plus the imaginary part squared. And the imaginary part is the part that multiplies j. So that's going to be 0.4 times omega. And we need to square that. So there's a couple of different ways we could do that. I guess we could put a constant and then put omega squared. So that might be the easiest way of doing it. So we have, again, the 0.4 squared, that'll be 0.16. And the omega squared will be that. So that's the imaginary part squared, the 0.4 squared times omega squared. Again, the j is nowhere to be found because that's not in the imaginary part. Okay, so we have the square of the real part plus the square of the imaginary part, and then we're taking square roots. That's how we take the, and again, in order to form that, we need to use brackets within brackets, which is allowed here. Okay, so now let's check that. And that is correct. And that's been printed on the screen here. A little bit easier to read notation using a square root. And now our next job is to approximate this function of omega in several different regions. So we can see that we're going to have basically different breakpoints. We're going to have a breakpoint here when omega is equal to 4 radians per second. And then we're going to have a breakpoint out here for this double pole corresponding to omega equal to 100 radians per second. So those are the breakpoints that have already been identified for you, although you should know how to do that in case you need to do this, of course, by hand. And so now we're going to approximate, for example, for omega much less than 4, then omega between 4 and 100, and omega much greater than 100. So for omega much less than 4, we look at this and see how we can approximate it. So if omega is much less than 4, then it's obviously also much less than 100. So basically the omega over 100 will be very small compared to the 1. So we basically just take that whole term and it becomes 1, so we can just essentially neglect it. Okay, so that term is gone. Now if omega is much less than 4 here, well, then this is basically omega over 4 quantity squared, if you will. So that, again, is going to be very small compared to the 1. So we're just going to have the 1 here. And basically, that's also going to be negligible in this case. And so what that boils down to is we're just going to have a 1 here. So we basically are just going to get 2 in this case. And so I'm just going to use the radio buttons here to select a constant, since it doesn't need a power of omega, and just enter a value of 2 there. Now we also need to convert that 2 to the value in decibels. And in decibels, remember that decibel units, first of all, we're always assuming that this is a voltage or current gain for these transfer functions. That should be assumed throughout this exercise. And remember that the formula for the number of decibels is 20 times the log to the base 10 of the magnitude. So basically we take the log of 2, we take 20 times the log to the base 10 of 2, and that works out to be 6.02 decibels. So in decibels, that's 6.02. You don't have to be probably quite that precise, but I'll just put it in like that. Okay, so now the next step would be to approximate in the second region, where omega is much greater than 4, we're going to assume, and we're going to assume it's also much less than 100. Now, sometimes those numbers might be a little bit close together where those approximations wouldn't necessarily be accurate, but we're still going to make them because in the spirit of making an asymptotic approximation, it will approach that line, even if it doesn't accurately represent it, not accurately represented by that line. In this case, they're fairly far apart, so we can do that. But we would always do it regardless, basically. So we're going to assume that omega is much greater, well, much less than 100, say, first of all, to look at this term. So that means that this is still negligible compared to 1 because omega is much less than 100, so this fraction basically is much less than 1. So we can, again, neglect that whole thing, and we just have a 2 in the numerator. But now we're going to assume that omega is much greater than 4. So basically that means that this is now large compared to 1. And in fact, because this is a 4th power omega and this is only squared, this will be the dominant term. So we basically have our omega over 4 to the 4th power, but then we're going to take the square root of that, so we basically end up with omega over 4 squared after we take the square root. So omega over 4 squared, that'll leave an omega squared in the denominator, and then the denominator being 4 squared or 16, that becomes into the numerator. So that's going to give us 16 times 2, or 32 in the numerator. So I'll enter 32 here. And then that's going to be omega to the negative 2, because that's over omega squared. So again, you can work that out on paper if you're more comfortable doing that. I usually do it just by looking at it. But again, the point is that this is the dominant term. And since that's basically omega over 4 all to the 4th power, then you basically just take the square root, it becomes squared, and then you flip it upside down to put it up here. Remember that this was neglected to be 1. Okay, so now we need to convert that to logarithmic units. So here we have to use the basic property of logarithms. Remember, it's 20 times the log of this is what's going to be over here in decimals. So 20 times the log of this, well, it's a log of a product of 32 and omega to the minus 2. And remember that the log of a product is, of course, the sum of the logs. It's the principal underlying slide rules, for example. So the log of 32 times 20, we just do that on our calculator. So that's 20 times the log of 32. And that is 30.10 decibels. So that's the constant term. And then the omega to the minus 2, when we take the log of that, that's going to bring a negative 2 using, again, the properties of logarithms. When you raise omega to a power, that's going to bring the power out in front of the logarithm. And that multiplies the 20 that's already out there. So that becomes a slope of negative 40 dBs per decade. And remember, that's called dBs per decade because as omega goes up by a factor of 10, that's going to increase the log of omega by 1. And therefore, then that multiplies the slope. So that gives us a slope of negative 40 dBs per decade. Okay, now in the third region, we have omega, and we're going to assume it's much greater than 100. So in this case, we're going to make a different approximation in this term, which is now that omega over 100 is much bigger than 1. So up until now, we've been assuming it's much smaller than 1, but now it's much bigger. So we're going to neglect the 1 to make that simple. And that means we're going to have 10,000 coming up into the numerator and then an omega squared here. So we're going to have basically 20,000 divided by omega squared. And if omega is much bigger than 100, then again, this will be the dominant term here, the 4th power term, because omega is now large. And so that's going to, once again, give us the omega over 4 quantity squared. So I'm just going to write that out on scratch paper for myself. So that was going to be 20,000 divided by the omega squared. And then we have the omega over 4 quantity squared, which is going to be 16 over omega squared. So now I need to multiply 16 by the 20,000. And of course that comes out to be 320,000. So our coefficient here is going to be 320,000. And then we have the omega squared times omega squared in the denominator, so it's going to be omega to the negative 4. Okay, remember that another pole will introduce a further change in the slope. It's a double pole. Okay, so that's our expression here. and then we need to take that 320,000 and take the 20 times the log to the base 10 of that number, and that works out to be 110.1 decibels. And then the -4, again, that comes out in front when we take the logarithm of this. And so the -4 multiplies the 20, and that becomes a slope of -80 decibels per decade. So there we get a pretty healthy negative slope. Okay, so that's the values, and now we'll check that. I hope that's all correct, and it is. Okay, so now those asymptotic approximations have been printed on here. They've been rounded off slightly, but that should still be adequate for our purposes. Okay, so now the next task is to fill in this table here, which contains the magnitude and actually the slope to the right of each breakpoint, and then we're going to, from that, use that to sketch the Bode plot. So the first break frequency, if you will, is at -infinity, or at least we consider that as break frequency here. And the slope to the right of that basically is the slope of this initial region, which is 0. As you see, it's a constant. It doesn't depend on omega, so that has 0 slope. In the second region, we see that the slope, it's just right there, it's -20 dBs per decade. So we just put in, I'm sorry, -40, I mean, -40. And then in the third region, again, is just -80. So we put that value in there. And the asymptotic magnitude at the breakpoint, well, at 4 radians per second, we're on the boundary between these two regions. And remember that these two asymptotic approximations will always intersect at those break frequencies. So we could use this expression, or we could use this one. We could put in 4 here and take its log to the base 10 and multiply by -40 and add to 30.1. But it's, of course, much easier just to use this one since that's already a number. So I'm just going to use this one as 6.02. Now, because that first pole at 4 radians per second, that corresponds to this quadratic term, remember that that's now asking me for the damping factor. And remember that's the 2 zeta times omega over omega naught. And so let's see, that's going to be, I have to use a piece of paper for that. So the 2 times zeta, because I've forgotten what it was now, divided by the omega naught is 4. That's equal to 0.4, and therefore that's going to be 0.8, it looks like. So 0 times 0.8, 0.4. No, sorry. Doing that wrong in my head. That's 1.6 divided by 2. Sorry, that's... Okay, let me just check that real quick. On my calculator, 0.4 times 4 divided by 2. Yeah, that's 0.8. Oh, yeah, that is correct. I was just confusing myself there. Okay, so the damping factor there looks like a 0.8. Okay, and then the next thing is this exact value minus the value at the asymptotic approximation. Now here, we're actually not going to have a lot of resonance because that's less, well, the damping factor here is over 0.707, which is where you would actually start getting a peak. But basically, you can use the approximation that will be the formula -20 log 2 zeta. So I'm going to take zeta times 2, and I'm going to take the logarithm of that and multiply times 20. And so that gives me 4. So the exact value minus the value intercept, that's going to be a negative 4.1 roughly. dBs. And again, that comes from the using the formula negative 20 times the log of 2 zeta decibels. Okay, or the other way, as I said, is you can just take omega equal to 4 and plug that into this formula and just evaluate that on your calculator, and then just compare that to this, subtract the asymptotic magnitude from the value that you get from evaluating it. So that may be a little bit more straightforward, but I'm using the approximate formula here. Okay, now at negative 80 dB, so at the next breakpoint, that's at 100 radians per second. That's on the border between these two asymptotic approximations. And so neither of those is a constant, so that's where I'm going to have to actually do some computation. So, but it's easy because the log of 100 is just 2. And so I have negative 80 plus 30.1. So that's just going to give me negative 49.9. And now at 100 I have a double pole, and so the exact value minus the value at the intercept for a double pole, for a single pole it would be negative 3 dBs, but for a double pole it's going to be negative 6. Now once again you could evaluate exactly here at omega equal to 100 and you get a little bit more accurate value than this, but this is going to be good enough. This does not have to actually be accurate to 1%. This 1% applies to these other entries. So that I'm just going to put in as a negative 6, and that should be plenty accurate for that. And having completed the table now, I'm going to go ahead and plot the curve just by putting the button. Now, of course, if you're doing this on paper, which would be probably a good exercise to do, you'd basically be using these data. So you'd say, well, I start out with 0 slope. I come to this value of the 6.02, so that's plotted here, up to the breakpoint of the 4 radians per second, which is right about here. And then you would have the slope of negative 40 dB, which takes you down to this value here, which is the negative 49.9. So again, you just plot a point on there, and then that's going to be a slope of negative 80 dBs per decade. So as you go up in one decade, like for example, in this case from 100 to 1000, then you should be going down by a total of 80 dB. So you can just take this value, negative 49, and subtract 80, and that would give you negative 120. Negative 129 dB, which is what that is there. Okay, so that's how you would plot that by hand. And having plotted that, and again, you're going to be the exact value is going to be lower than these intersects. So this exact curve is going to come in here like this, and then it's going to come in here like this. Now, it could go above there if you had a small damping coefficient, like if zeta was, well, certainly a number less than 0.7 to get a peak. Although actually, well, if a small value of zeta basically is going to give you a big peak here, so that would be different. But we don't have that small value of zeta in this case. So now let's check the answer. And that is correct, and it shows you that again, this is, in this case, going to be negative. Now it's possible to get a positive value for this deviation. Again, if you have a small value of zeta, then this might have actually come out to be instead of minus, this could have been a positive number because you could have had a resonant peak. But that's only going to happen, again, for relatively small values of the damping coefficient. Okay, so there's the exact curve generated by the computer. And if you want, you can change the axes here to see on linear, horizontal, or vertical axes just to get a better idea for that. But basically, that does complete the hard example.